Hi students, in this session we will discuss about formulation of stiffness matrix, formulation of load vector, assembling of global equation and a simple problem with axial bar element. Okay, hope you all understand general steps in FEM. Hope you all remember that. The first step is discretization of the structure, where we will divide a structure into small pieces of elements, and again after discretization we will number the nodes and these elements, and after that we will select the displacement function or shape function or interpolation function. Then we will define the material behavior. After that comes derivation of elemental stiffness matrix. So let's see what is stiffness matrix and how to derive the elemental stiffness matrix. Okay, in order to get an expression for the stiffness matrix in finite element method, let us review a strain energy expression in structural mechanics. There is an equation of stiffness matrix K is equal to integral of uh, matrix strain displacement matrix transpose into stress strain relationship matrix into strain displacement relationship matrix into dV. That is the equation. K, the matrix K is equal to integral of matrix B transpose matrix D matrix B into dV. So in one dimensional problem, we are dealing with one dimensional problems. So the strain is equal to E is equal to du by dx. You know, where u is the displacement function. And in one dimensional problem, the elasticity matrix, that is stress strain relationship matrix, is equal to Young's modulus. For beam problems, it is this stress strain relationship matrix, that is D is the flexural rigidity. Okay. So we are dealing with one dimensional problems only. So consider a one dimensional bar element with node 1 and 2 as shown in figure. You can see in figure of a bar element have two nodes 1 and 2 with respective displacement u1 and u2 having length L bar. So already you know that in one dimensional bar element displacement function is represented as u is equal to n1 u1 plus n2 u2, where n1 and n2 are the shape functions. Hope you all remember that n1 is L minus x by L and n2 is x by L. So the strain displacement matrix B, which is defined as, is equal to matrix of differential of this shape function with respect to x, d n1x and d n2 by dx. So we will differentiate n1 and n2 with respect of x, and we will get the b, that is the in equation K is equal to integral of b, that b, the strain displacement matrix, we will get. And after we getting the b, the strain displacement matrix, we will transpose it. So which is used, which we need to substitute. Okay, for one dimensional problem we already mentioned D, or elasticity matrix, is Young's modulus. So we will substitute these all in the equation, the main equation K is equal to the stiffness matrix equation. Okay, after substituting this limit is from 0 to L, because the bar element we consider is of length L. So we have to integrate it from 0 to L, and dV we can represent it as A into dx. So we will substitute that also, then we will multiply the matrix and we will get the 2 by 2 matrix. Okay, from there by keeping dx alone, other things we will take it outside and we will integrate dx with respect to x. So the integration is x from 0 to L. So we will substitute the limits also, and at last we will get the equation for stiffness matrix for one dimensional bar element is K is equal to AE by L into a matrix of 1 minus 1 minus 1 and 1, which is a symmetric matrix, isn't it? So note that stiffness matrix is a symmetric matrix and sum of the elements in any column is equal to 0. And when these elemental equations are assembled and we will get a global stiffness matrix equation. So that global stiffness matrix dimension is n cross n if number of nodes are n. We will see this point later, and we know that general force equation F is equal to K into U, where F is the force vector, K is the stiffness matrix, and U is the nodal displacement. Okay. For one dimensional bar element, the stiffness matrix we have already derived, K is equal to AE by L into the matrix of 1 minus 1 minus 1 1. For two noded bar element, you can write the force vector and this nodal displacement vector in two dimensional form, means two noded form. So you can write it as F1 F2 is equal to AE by L matrix of 1 minus 1 minus 1 1 into matrix of U1 U2. So this is the finite element equation for one dimensional two noded bar element. Okay, and let's see how we will assemble the stiffness equation. Consider a bar, and this bar can be equally divided into four elements, so we will discretize it into four elements, and I have numbered 1 2 3 4 for the four elements, and the nodes with the red marking 1 2 3 4 5. So now the bar has four elements with 5 nodes. For a two noded bar element, the equation is the same equation, F1 F2 is equal to AE by L into 1 minus 1 minus 1 1 is the matrix into U1 and U2 is the matrix. Okay, so 1 is the force vector matrix, that is force vector matrix is equal to stiffness matrix into displacement matrix. Okay, so think we discretized the element into 4. So consider one element which have two nodes, isn't it? Element 1 have two nodes, element 2 have two nodes, element 3 have three nodes, two nodes, sorry. So two nodes. So you can apply this two noded bar element equation everywhere. For one element 1 having node 1 and 2, we will apply this equation. For element 2 having node 2 and 3, we will apply the same equation. For element 3 having node 3 and 4, we will apply the same equation. So after applying this for element 1 2 and 3 and 4, we will combine this. So you can see that I have marked A11, A12, A21, A22 for each element 1, element 2, element 3, element 4. Element 1 is A11, A12, A21, A22. Element 2 is written as A22, A23, A32 and A33. Now we will combine this. See, while combining A11, A12, A21, A22, then A22 we have 1 plus 1, isn't it? This 1 plus 1 come from, 1 is from element 1, A22, and 1 is from element 2, A22. So like that we will compile. So the global matrix, global stiffness matrix will be getting. Assembling the equation, we will get the global stiffness matrix equation. So that is K is the global stiffness matrix, K global. Okay. And now let me remind you something. This one, n into n is the dimension of the global stiffness matrix, where n equal to number of nodes. You see, here we discretized the element in four, the whole structure into 4 elements, and we got a 5 nodes, isn't it? So the global stiffness matrix will be having 5 cross 5. That's it. Okay. So here the force vector, a load vector or force vector is equal to stiffness matrix into displacement matrix. Okay. So how to formulate the formulation of load vector? Consider a vertically hanging bar of length L, uniform cross section A, density rho and Young's modulus E. So this bar is subjected to a self weight. Consider it as X. The elemental nodal force vector is given by F is equal to integral of shape functions matrix transpose into self weight. So we know that self weight due to loading force is rho into A into dx. You can substitute that in the first equation. For one dimensional bar element, you know displacement function is u is equal to n1 u1 plus n2 u2. We have already discussed about it, where n1 is L minus x by L and n2 is x by L. Now we can write it in matrix form n, and we will take the n transpose, since in equation we need the n transpose. We will substitute that and we will integrate to 0 to L. So from 0 to L we integrate, and we will get as force vector is equal to rho AL by 2 into a matrix of 1 1. Okay, this is the force vector. So this force vector is equal to this global stiffness matrix into the displacement function. This is how we will assemble the whole equation. The confusions will be over when we discuss the problem. Simple problem, we will discuss one simple problem, and similar problem you can get it in textbooks and the notes. Okay, let's consider a bar. An axial load of 200 kilonewton is applied at a point P. Take it is given that A1 area of element 1, Young's modulus A2 and its Young's modulus is given. So element 1 and 2, there are two elements, so three nodes will be having. Okay, so calculate the nodal displacement at point P. At point P we need to calculate the nodal displacement, stress in each material and reaction force. So when a problem is given, the first one is you will mark the elements and nodes. Okay, the element 1 and element 2, and there are three nodes, node 1, node 2 and node 3. So given that area of element 1 is 2400 mm square, area of element 2 is 600 mm square, the length of the element L1 is 300 mm, L2 is 400 mm, and Young's modulus of element 1 is 70 into 10 raised to 3 Newton per mm square, and Young's modulus of element 2 is 200 into 10 raised to 3 Newton per mm square. Okay, point load at P is 200 kilonewton, it is also given. So we need to find nodal displacement at point. Okay, P, that is U2, stress in each element is sigma 1 and sigma 2, and reaction force R1 and R2. So let us see how we will start. We'll start with the finite element equation for one dimensional two noded bar element, isn't it? That is, the equation is, you are familiar with the equation, the force vector matrix F1 F2 is equal to AE by L into the matrix 1 minus 1 minus 1 1, that is the whole thing called as stiffness matrix, into the displacement matrix U1 U2. Okay, now consider the element 1 only. When you consider the element 1 only, it consists of two nodes 1 and 2. So F1 and F2 comes under it. You will substitute A, E and L into the equation and you will frame equation 1. Similarly, for element 2 of having nodes 2 and 3, you will substitute respective A2, E2 and L2. You will calculate and you will formulate the equation as 2. Okay, then we will assemble the equation. So while assembling the equation, you can see that A11, A12, A21, A22, 5.6 minus 5.6 minus 5.6, 5.6. And in element 2, you can see 3 minus 3 minus 3 and 3. When you assemble it at N22, at A22, you will get 5.6 plus 3, isn't it? This is the assembling. assembling of two elements, isn't it? Two elements. So three noded two elements. We will assemble it and we will get the equation. Now note that the bar has three nodes. Each node has single degree of freedom. So global stiffness matrix is of size 3 cross 3. So this I already mentioned. The global stiffness matrix will be having the matrix size of number of nodes. Here number of nodes is 3. So the global stiffness matrix will be having 3 cross 3. Okay. The properties of stiffness matrix are also satisfied. That is, stiffness matrix is a symmetric matrix, yes, and the sum of the elements in any column is equal to 0. You can see 5.6 plus minus 5.6 is 0, minus 3 plus 3 is equal to 0, minus 5.6 plus 8.6 minus 3 is equal to 0. So it also satisfies the stiffness matrix properties. Now after that we will implement boundary condition or apply the boundary condition. So first we want to find nodal displacement at point P. At point P, U2. So displacement at node 1 and 3 are 0. So you can write U1 and U3. We can substitute U1 and U3 equal to 0. A load of 200 into 10 raised to n, 10 raised to 3 Newton is acting at node 2, and a self, and F2 is the force. F2 is given 200 into 10 raised to 3. So self weight is neglected. That is F1 is equal to F3 is equal to 0. So we can substitute U1 and U3 equal to 0, F1 and F3 is equal to 0. Then this this third equation get reduced like this. Okay. And in this equation at U1 is equal to 0. So we will do, when we do the matrix, we will neglect the first row and first column, and U3 is also equal to 0. We will neglect the third row and third column. So directly we will get the U2, that is nodal displacement at 2.2. Okay. And now the second thing is we need to find stress in each element. So stress is equal to E du by dx. For first element, when we substitute, sigma 1 is equal to E1 into U2 minus U1 divided by L1. We will the whole things that is sigma 1 we need to find, E1 already, U2 we have found right now, and U1 is given and L1 is given. So directly we will get stress of element 1, and similarly the stress of element 2 also. So here we get stress of element 1 as tensile and stress of element 2 as compressive. Okay. The reaction force equation, there is a force equation, reaction force equation, R is equal to K into U into minus F. Okay. Reaction, the force is a reaction force, so stiffness matrix into displacement matrix minus the force matrix. So everything we know, K, the whole thing K into U, we already found it. We will substitute that, and direct substitution we will get the results R1, R2 and R3, that are the reaction forces at node 1, 2 and 3. So the results are nodal displacement U2 we have found, stresses in each element sigma 1 and sigma 2 we have found, and the reaction force R1 and R3 we have found. Okay. This is how we should do a problem relating to one-dimensional bar element. Okay. This is an example for one-dimensional bar element having one dimension, three-noded bar element. Okay. So similarly, you should prepare to do the problems. So firstly, you should thorough the steps, general steps of the FEM. What is shape function, the shape function equation, then comes the stiffness matrix, then comes the formulation of load vector, assembly of global equation, and after that implementation of boundary conditions. Okay, hope you all understand the fifth module, the concept of FEA or FEM, finite element method. Study well, students. Thank you.